In this lesson, we're going to learn how to analyze algorithms and look at what we call the time complexity of them and be able to tell on a given algorithm how much, how much complexity there is, and given two algorithms, which one might take more time than the other. So that's the kind of thing that we're talking about here. So first of all, let's talk about computational complexity. That's the amount of resources used by an algorithm. So the primary resources that we need to optimize for this within this computational complexity would be the time complexity, which is the amount of time the algorithm requires in order to be able to execute, and then the amount of memory used. That's the space complexity. And so those are the two that are the most important as far as needing to optimize for running an algorithm. And each of them would be determined by the size of the input. And we'll see some examples so you'll kind of get the idea what I mean by that here in a little bit. Now we're just going to focus on the time complexity, so we won't be worrying about space complexity, but just time complexity. So first of all, we're going to learn how to come up with a time complexity for a given algorithm, and that's going to be, we're going to call it the time complexity function. We'll be looking at an algorithm coming up with a function that describes the time complexity. So here's what this says. It says the time complexity of an algorithm is defined by a function. This function is going to have a domain of positive integers and a range of positive integers, such that f of n, which is this time complexity function, is the maximum number of atomic operations performed by the algorithm on any input of size n. And then it goes on to say that what z plus is, and that's the positive integers. So that's the official definition of time complexity. So remember, as we are considering time complexity, we are going to be finding the maximum number of atomic operations performed by the algorithm on any input of size n. So if we take a look at an algorithm, we're going to try to count the number of atomic operations that might possibly be done, the maximum number, the worst case scenario. We're going to add those all up, and then we'll come up with a function called the time complexity function. So let's take a look at this algorithm here. You see it's a simple algorithm where we're adding up some numbers. We're putting in n numbers, a sub 1 up through a sub n, adding all of those up, and then going to return that sum. So let's see if we can count here. So first of all, this first statement here is an assignment operation, so we could count that as 1. Now we've got a loop. That loop's going from 1 up to n, so we would know that would be performed n times. But how many operations are done each time that loop is performed? Well, in each iteration, we have these things going on. First of all, that for loop has to test the value of I at any given point, and if it's still in the range, then it will continue on. So that test has to happen, and then also it's going to need to increment by 1 each time it goes through. So we could count that as 2 operations. Then inside here, inside the loop, we've got this sum equals sum plus a sub I, and that would involve 2 operations because we're adding sum plus a sub I, and then we're assigning that to sum. So we're an assignment operation plus an addition operation, so that would be 2 of them. Okay, so then at the very end, we have return sum. So that would be 1 operation there. So let's see if we could add them up. Well, let me see if I can write this out a little better here. So this whole thing here, that loop, is going to be performed n times, but inside that we've got 4 operations. So if we were to add all this up, and here's, oh sorry, let me just do this, 1 and 1. So what are we going to have? We're going to have 1 plus 4 times n plus a 1. And that's what we have right here at the very bottom. A 1 plus a 4 times n plus a 1. And that simplifies to 4n plus 2. So we would say that the time complexity function is 4n plus 2. Well, what if we care about the asymptotic growth of that? As n gets big, how is that going to act? Well, we know that 4n plus 2 would be of the order n. So we would say, 4n plus 2 is theta n. And so besides coming up with that time complexity function, we're also wanting to find the order, because that's really what we care about, is how quickly does that time complexity grow as we increase the number of our input values. The book has this chart here that shows these different growth rates for different input sizes. And by the way, I guess I should read this sentence up above. The asymptotic time complexity of an algorithm is the rate of asymptotic growth of the algorithm's time complexity function f of n. So we had found that in the last slide that we found the time complexity function and then went ahead and found the asymptotic growth of that function, and that then would be called the asymptotic time complexity. Okay, so anyway, this chart here, they've shown some different functions that might represent some time complexity functions for different algorithms. And they've shown how the amount of time would increase based upon the number of n. Now, this is all assuming that one single instruction would take 1 microsecond to be performed on a computer. So if we just had a function like that one that we just saw, which was theta of n, we'd see that if we put in, this is the one that's circled here in red, if we put in 10 numbers, that would take 10 microseconds. 100 numbers, 100 microseconds, and you see that if we put in 100,000, it would still be just 0.1 second. But if we had another algorithm that had a more, an asymptotic time complexity that is of a higher order, we can see how much this would, make a difference. So let's say we have something of order n squared. We could start out with just 10. It would be 0.1 milliseconds. But if we had 100,000, it would take 2.8 hours. But if we just go up to n to the third, then to do 100,000, to have 100,000 input values, it would take 31.7 years. So they're just showing how how the time complexity can really make a difference. When we're looking at 2 different algorithms, one might just take very little time, another one could take a lot of time because it would have a higher order of time complexity. Let's take a look at this one. This algorithm, let's see if we can add up the atomic operations and then come up with the asymptotic time complexity by finding the asymptotic growth of that time complexity function. Okay, so average of n's. We're going to be putting in again a sequence of numbers, and we're going to output the average of the first and the last elements in the sequence, not the lowest and the highest. It's not going to even try to order them. It's just going to say the first number that was put in and the last number that was put in, add those two together. So first of all, we have sum equals A1 plus A2. Well, that's just two operations because we're adding and then have an assignment. Now the next one, same kind of thing, we're doing a division and then making an assignment, so that's two operations. Then this last one is one operation for returning. Notice none of these depend upon n. We didn't have a loop in there. We're just going through these three little statements. So if we add up how many there are, 2 plus 2 plus 1 gives us 5. So we'd say that the time complexity is f of n equals 5. So the asymptotic time complexity then would be theta of 1. So you see that that does not grow at all as n gets bigger. So I could put in 100,000 numbers and the time complexity does not change. It's just going to be the same no matter how many numbers I put in. So here's an example I wanted to talk with you about. You'll see in your participation activity, it'll walk you through this. But I wanted to make a couple of points about this. First of all, you can see what this is doing is it's an algorithm that's finding the smallest number in a sequence. And so you could probably follow all along what they're saying here, but something that's different here is that we have an if statement inside that loop. And so it says if a sub I is less than the minimum, then do this assignment operation. So every time you go through the loop, that assignment operation is not always going to happen. It might happen if that condition is true, or it might not. So for that line, either we're just doing a comparison and that's all, or we're going to do the comparison and make that assignment. So in the worst case, for the actual input, let's say that the smallest number was at the very end. Then every single time we go through this, or let's say that they're ordered in descending order, then every time we go through that, it's going to be making this assignment. So that would be the worst case. But if they were put in ascending order, then this assignment wouldn't be ever done at all. So it kind of depends upon the actual input values as to how many times this is going to happen. So what we'll do is assume the worst. And so we could add that up and say, yeah, let's assume the worst, that one operation, that assignment operation would happen all the time just to get the worst case. Okay. Now, you see over to the right, they say constant C operations per iteration. C is equal to 3 or 4, depending on the input values. So, yeah, for the worst case, we would say it's 4, but sometimes it's 3. But now, here's the deal. It really doesn't matter if we count that as 3 or 4, or even if that, not all operations really would take the same amount of time anyway. So are they really equal, and do we really need to be adding these up meticulously like this? It turns out not. If it's 3 or 4, or 5 or 6, whatever, we could just say it's some constant value. And the reason why we don't care the difference between 3 or 4 or 5 or 6 is that when we find the time complexity, and then we find the asymptotic growth of that time complexity, the constants end up being irrelevant, right? Every time we look at a function and find the order of that function, it doesn't matter if there's a 4 in there or 100 in there, unless it's a 4 or 100 as an exponent, right? That would be that would be different, but exponent on the n value. But if we just like have something, you know, a multiple of a term, we've seen in the past, in the last section, we didn't care, you know, if we have 4n plus 3, and then, you know, it would be of order n. And we don't care if that was a 4 or if it was a 400 or whatever. So what they start doing at this point is saying, yeah, we can add them up, but let's just call it a constant c, and we won't really worry about how many times, okay? So they say, yeah, that that loop there is going to be just a constant that we're going to be worrying about. So here this is n minus 1 times, because we're going from 2 to n, and inside we're just going to say, let's just call that c. Sorry, you can't really see that very well. Okay, and then we have these other two here, this one here and that one there, which we could add up to be 2. But they say, well, again, you know, let's just not worry about the number and just say it's some constant d. So that's how we get n minus 1 times c here. It's c inside that n minus 1 loop there, plus the d. Then we could simplify that. We get a function here. And again, we don't necessarily care about this time function. We want to know what's the asymptotic growth of the time function. And we see that it would be of order n. We have f of n is theta of n. And again, notice, see, it doesn't even matter what we came up with as those constants. It's just going to end up only in depending upon that expression that involves the n and the factor that involves the n. Okay, so anyway, that hopefully kind of convinces you we don't need to always be so careful in adding up. Is that a 1 or a 2? We'll just say it's some constant, and that's all we care about. Here's another example, and at this point I wanted to say that in the book they start talking about the worst case time complexity function. And this is what they say. The worst case time complexity function is defined to be the maximum number of atomic operations the algorithm requires, where the maximum is taken over all inputs of size n. So I don't know. I don't know if I'm missing something or what, but to me this seems like that's already built into the definition of time complexity, because time complexity says it's the function such that the function is the maximum number of atomic operations performed by the algorithm on any input of size n. So anyway, the author then starts to really kind of spend a lot of time thinking, well, what's the worst case as opposed to not the worst case? But in my thinking, all we need to care about is the worst case. So anyway, the point I want to make is let's not worry about, I'll just kind of go on here and say, so in this example here, they're gonna look at, find there at the bottom, they're going to say, okay, f of n is equal to this, and it's O of n, and then the worst case is omega of n and all of that. And I just wanted to tell you, I don't think you need to be worried about that. And so just go ahead. When they try to find an upper bound for the worst case and a lower bound for the worst case, so that they can find a function, you know, that's the actual order, just ignore that. When the author finds a time complexity function and then starts to try to show an upper bound and a lower bound, ignore it. Again, I feel like all we need to do is find the time complexity function and then determine the order of that function, and that's all we need to do. So for this one, this example here, again, we would just, I think we should just do it like we did in the past, which is just find that time complexity function. So it would be f of n equals 4n minus 1, and therefore it's theta of n. Let's look at another example. In this case, we have 3 sequences that are input. All of them are of length n. And we're going to go through these steps here. So let's take a look and see what we would have for a time complexity function. So for this first line here, we'd say, well, that's just one atomic operation. But again, we're just going to say, I don't even really care. Is it 1, 2, 5, or 10? We're just going to say it's a constant number. So let's just call it b. Then inside this loop here, we go from 2 to n. So we're going to be having n minus 1 iterations of that loop. Inside the loop, this would be one where, it kind of depends, since we have this if statement here. Sometimes it might do a certain amount, sometimes it might do another. Again, it doesn't really matter. We could say what's the worst case, but again, we'll just say it's some constant number, so we'll call it C operations. Then down here, D operations. We're just coming up with letters to use for these constants. Another loop that has n minus 1 iterations. And inside there, let's just say there's M operations. I'm not sure how I got or they got the, why we went B, C, D, and now all of a sudden M, but that's what's there. I don't remember if I came up with this or the book did. But anyway, we'll call it M. And so there's M operations being done n minus 1 times. Here, let's just say P operations and n minus 1 iterations of the loop. And inside there, just say Q. Again, just a constant number. And then at the end, the output, let's just call that R, a certain constant again. So all of these are constants except for those iterations, the number of times. So let's look and see how we would end up with this function that you see here. So remember that this loop here, we're saying that C operations are being done n minus 1 times. So that's how we get this, C being done n minus 1 times. So we've got the B plus C times n minus 1 plus a D, and then plus, and then here, that loop is being, M operations are being done n minus 1 times. So that's why we get that right there. And then plus P, and then again, Q being done n minus 1 times, so we get this. Plus R then. Okay, so you see how we come up with that. Now we could simplify this a little bit. Remember what we care about here, we have all these letters here. The only letters that are the letter that is the most important is the N, right? Because all of these others just represent 2s and 3s and that kind of thing. But we're going to simplify this a little bit, combine like terms so that we can get it down to having, all the constants kind of put together, and that will be a constant within itself and so on. So let's first of all take these terms that involve an N, and we can combine all of those. And then also take the terms that don't involve n, and we could combine all of those. And so we're going to get, a certain number of n's when we put all of those terms with an n in there, and then a certain other constant that's just by itself that doesn't involve n. So I'm not even going to try to say what that is. It would be, for the constant for that second box, it would just be B minus C plus D minus M plus P minus Q plus R, right? Those are all the constants. Put all those together. That would go in that second box. But I'm not even going to write that out. We just know that's a constant. So I just kind of put empty boxes, but imagine that there's constants in there. So if that's the time complexity, what's the asymptotic time complexity? And that's going to just be theta of n, because there's an n, some constant in front, and we really, again, this just shows we don't really care what that constant is. And then a constant by itself, which ends up disappearing. So we would say that is the asymptotic time complexity of this algorithm. Here's one more. So we've got, in this case, a loop within a loop within a loop. So let's see if we can figure this out. Again, we're going to have three sequences, one sequence called A's, and then the B's and the C's, but they're all of length n. So if you take a look, let's kind of start in the middle and move out, because let's look inside that that inner loop, the K loop. So we could say that there's B operations inside that K loop. So again, that would include the checking of the K, the incrementing of the K, and then checking this if statement, and then possibly making this assignment. So add all that up, we'll just say that's a constant B. But that's being done n times because there's n iterations of the loop. Now and then I guess for here we're going to go ahead and talk about that last line, which is C operations. But now, okay, now we just talked about that K loop, but that K loop is inside a J loop, and that J loop is going to be done n times, and then all of that is inside an I loop, and that's going to be done I times. So here's what we get, and I'm going to show you how we got this, and you can probably see right off, but I'm going to go ahead and show you. So if we start in the middle and say there's B, and then but the K loop is iterated n times, so it would be n times B for that K loop. So that's the K loop, but those statements are performed n times because of the J loop. So I'd put an n in front of there. That's how many things are being done if we consider the K and the J loop, but that's the number of things inside the I loop. So then they're just putting a bunch of parentheses here. So we get that. And then at the end we have plus C. Sorry for my writing. I'm still trying to get a situation going where I can write a little bit more better than this. Now if we multiply all of those n's together, we get n to the third, and that's being multiplied by the b, and then we have plus c. So we see that that function will be theta of n to the third. Again, in the book, when you see them trying to show there's an upper bound and a lower bound, just ignore that. In my mind, all we need to do is find the time complexity and then determine of that the order of the time complexity. And so that's what we just did right here. I'd like to make an observation here. If you take a look at the examples that I've shown you and then those also in the book, you will see ultimately after all of the analysis of finding out is it, B, NB plus C or whatever, all of that, which I want you to be able to do for fairly simple algorithms. But ultimately, after doing all of this, we would find there's a pattern, and it comes down to then making this actually very simple. If we have an algorithm with simple loops, what I mean by simple loops is we don't have a loop inside a loop, but just like a loop 1 to n, something like that. It's a loop that involves n, or maybe there's more than one of them, but they're not inside each other. Then that algorithm is going to have an asymptotic time complexity function of the order n. It'll be theta of n. But if we have an algorithm with a loop inside a loop, then it's going to have that asymptotic time complexity of the order n squared. Okay, and then we saw an example where we had a loop inside a loop inside a loop. It was like a 3-level loop there. Well, that ended up having the asymptotic time complexity function of order n to the third. So that's a general rule that where now, and I think they will ask you, they'll give you an algorithm, and that's really, if they're only asking you what's the order, it's theta of what, then this is what you want to take, um, this is what you want to think about in coming up with your answer. And then, we did see some algorithms that had no loops that involved n. There could be a loop going from 1 to 3 or something like that, but that doesn't involve n. But if there's no loops at all that involve n, then it's going to be that time complexity, asymptotic time complexity is going to be of order 1. So anyway, keep that in mind. It ultimately comes down to really this. Although, it's important that you did follow what I've said up until now so that you kind of see how we get to this final result. So for this week, I'd like you to do all participation activities and all challenge activities from these two sections that we just covered. So it's the asymptotic growth of functions and the analysis of algorithms. So do all of those, and those will again be due by next Monday at midnight. Let me know if you have any questions. Email me, or well, that'd probably be the best. Email me and we can meet and talk on Zoom, or if you just have a question that you want to ask me by email, I'll be glad to try to answer it that way too.